Oh, that's funny. It's like this problem right here. Oh, actually, it gives it to you already. So that's the one, and then the long skin. And this guy would be, let's see, E of t, t plus 1, E of t, and 1. Non-zero independent, non-zero independent. This guy would be C1 E of t plus C2 t plus 1. You already know this one. So it's minus y1, y2, rt, and Wronskian of r1, ry1, y2, plus y2, 1 rt, that's the Wronskian of y1, y2, d of t, d of t. T plus 1, t divided by c of t dt plus t plus 1 e of t divided by minus t of t dt. Then to just do the integral e of t plus 1, t plus 1, t cancels out. This is positive now, and e minus t dt minus t plus 1. This cancels out with this guy. This is going to be dt, right? This guy cancels with that guy. E of t minus e minus t plus 2 minus t plus 1 times t. So y p of t equals minus t squared 2t minus 2. So you have this, and therefore y of t equals y of c, t plus y of p of t, y of t then equals c1 e of t plus c2 t plus 1 t squared minus 2t minus 2. I think we're done with this one. This one, we'll cover that one. 6x. I mean, you could technically do this one. Non-zero versus linear dependent. Okay. 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 Reduction of order, what else? Repeated roots, complex roots, real and distinct roots, basic concepts. Euler's method. Bernoulli differential equations. This is the one. Yo, how you doing, man?
Yeah, pretty good. How are you?
How was the writing?
Yeah, it went okay at the end. It was real
That's good.
difficult, but I was able to kind of figure it out.
Yeah, I knew you could do it. It's how long was how many words was it?
It was 830 words or something like that.
Okay. And you guys were given like a topic and then
Yeah, it was kind of like I I don't really exactly know how to explain, but it's like explain anything that is something that can't be expressed in your in your transcript or your
I see.
information that
It's kind
makes
of like a
you
cover letter.
different kind of thing.
It's like
It's a
some like
statement of purpose.
yeah, in essence, yeah, that's what that is. SOP. A lot
Mhm.
of times, yeah, you have to really. I've written those before. You have to direct your kind of like tailor everything together, and
Yeah.
it's like your cover page, and you let them know it's like
Yeah.
why.
Your cover letter, pretty much.
Yeah, it's not
Graduate
bad.
school stuff.
Yeah, it's not bad. I feel like did you already take the JRE by the way?
The JRE.
Yeah.
No, I have not. Not yet.
Is it required still?
I think so. I think the GRE for graduate school is required.
Okay, yeah, because the whole thing with I heard some schools are like not they're actually waiving it, but then there's some other ones who's like, oh, okay. I heard this from her like, oh, you have to take it because you can still take it online, you know.
Yeah, because I mean, I still have a good number of classes left to take, so it's not like I'm transferring to graduate school. I wish I
Yeah.
was, but I'm just transferring to hopefully to a place where I can finish my bachelor's
Other
and then
okay,
go have a little easier time
and
getting into
transition
graduate school. Yeah.
and transitioning. Yeah, that's
Yeah.
that's a good idea actually. If you do that, then oftentimes yeah, they some schools actually have like a bachelor, you know, like a 4+1. That they have
Mhm.
it like a 4+1 where it's not you could actually do both your BS and MS together.
Interesting. Okay.
Yeah, some schools do that, which is like only 1 year. Even with that, you like that 1 year is like the maximum. You could actually do it in maybe half the year, 6 months, if you
Wow.
have enough credits.
Yeah.
Which is like the best thing because you can move on, you know.
hmm
Yeah. Okay. Did you get a chance to look at the? I think so. The exam is still. You said still on Friday, right?
Yes, it's on Friday.
Okay. I think with what we have, if you already did some of the, did you finish all the problems?
No.
Okay. How far did you get?
Uh, it's I've I have this. It's because I've been working, I guess, trying to get to through the physical chemistry stuff because the exam is tomorrow.
Oh yeah, yeah, yeah. It's and then that one, is it written or is it oral?
It's written.
Okay.
What I think I could do is I could definitely go through the problems because I mean Wednesday and then I have you know 2 full days to do the exam
Yeah.
prep. So
Okay.
I don't
That's
know.
the. I think for what I'm thinking is what like trying to like review kind of like graphs about everything we've covered so far. I know I
Okay.
remember obviously the we covered them like deeply in other sessions. Which ones are you like the one that I want to cover today is this VOP,
Okay.
the variation of parameters, which we haven't covered yet. But like
Yeah.
besides this, were there ones that you seem to be not confident about, and then maybe we can
Um,
cover more on Thursday.
yes, definitely. It would be the identifying the type of function
Let me
using
write this down.
the
Let me
Leholi Bernoulli.
the Bernoulli one.
Yeah, just I because it's like
Equation.
it's the one where it's just a table and it asks you to
I think I
write
know what you're
in,
talking about. Yeah, like which one are they?
yeah, which one are they? And that I feel like if I can identify that, then it will help me kind of get a majority of I
There
guess,
was
the
a
way through.
there was another one there besides Bernoulli. There was one that I wasn't like. It's a little weird, like the wording. I know there was linear, non-linear, and
Yeah,
then like
linear,
let me look
nonlinear,
into
linear first or zero order, and then
this one right here. I actually
yeah,
I
all
kind of
those.
I kind of circled it because I knew like this one was gonna come up. So you have the Bernoulli one, and this is just a form. It's just a form that you have to fit it, like that you have to look for.
Yeah, but it's like all those
And then
trying to
this one,
classify
I think
because
this one's a little weird. We didn't see this one yet. The integrable,
mhm. Yeah,
separable.
he
You know
meant to
about this one,
put in
right?
the linear one in the question problem, like in the question itself.
Okay.
So it's actually 7 things, and I need a lot of help with identifying a good way to identify which equation fits which of the 7.
Okay. Well, we'll see like what we can cover. But some of these you know already, right? You know what linear, nonlinear is kind of. This is, and then
I
the
mean, that's the y double prime, and then
yeah,
the single prime.
this one is like when you have things the dependent variable. If this one is being raised to like a 2 plus,
Yeah.
this is like this is nonlinear.
because
And
you
then
can't get 0.
yeah, and then linear would be when this is like just one.
Hmm.
And then also like if the dependent variable is inside like a treg or like any of those E functions, transcendental functions.
Yeah.
Then this is also nonlinear. And then like what's it called? The separable one is when you can separate y and x, right?
Yeah.
You can separate y and x, and then also the exact. What about that one? Exact.
Exact. I don't know, because I do remember he was mentioning things like you would have an M, X, and Y,
You're talking
or
about this guy right here. This guy
yeah,
plus
MXY plus NXY. Yeah.
dy dx equals 0. Yeah, if you can fit it. Also the Bernoulli. So this is exact. And then like just understanding that that's
And then
there's
partials, I think, is
there's a bunch
Bernoulli.
there's a bunch of we can cover that one like
Okay.
what they are and classifying it.
Yeah, every single one, not just Bernoulli, but like I classifying each type too.
Okay. Yeah,
That
there's a procedure for this, so this is
okay.
a good one. And then the Bernoulli one, just to like write the equation down. The Bernoulli also has a form which is this
Partials.
one, right? This guy right here, y prime plus like p of
Oh,
x
yeah.
partial. Did he talk about partial?
Um, yes, he did. The partial is where, yeah, it's like an F partial X, G partial Y or something like that.
Is that let me see. Is this the Bernoulli one?
I don't remember. I would think so.
Let me see. I thought that was like the one with the integrable. If it's integrable, it
Then that
might
would
be
just be integrable then, not
that
Bernoulli.
that one would be when you can like specifically write it in a form where it's like f. It's like something like this, and then this one is like some type of function, something like this. If it's like you can write it in this kind of form, it's
Mhm.
integrable. But okay, that one we'll look into doing that. That one
Yeah.
I
Putting
think
it into normal form.
normal form.
I think it's called normal form, but the form you have to sometimes convert that what you're given into a specific form to then from there identify which of the 7 it is.
Do you have like a quiz or homework that has that or lecture?
I don't know in particular which one,
Because that
but
would be good if we do cover that, like kind of the same way as what the professor, how the way that you guys are doing it.
I'll have to see.
Oh, I think I know what you're talking about. So the Bernoulli one actually has this one as well. You're talking about this guy, right? This is Bernoulli.
I'm sorry, I had the screen minimized trying to find this stuff.
Okay, it's
Could you
all
show
good.
me what you were referring to or
This
writing?
one.
That one? Oh, I think
Substitution. Like this is where you do substitution looking at Bernoulli equations. Something like that.
substitution of Bernoulli. Okay.
So first and second, okay, that shouldn't be that bad. I think mainly if we cover this, like each one of these guys, how to classify them, the ones that we didn't cover yet, I think that should cover some ground.
Hmm.
Did you guys do intervals of validity? Is that familiar? Intervals of validity? I didn't really see that in here.
That sounds unfamiliar.
Okay, so we're not doing it. That's something we covered in before. Not here, but like I've heard that term.
Is it like a boundary value type problem, or
It's just it just
because
gives it like yeah, it's a value IVP. Yeah, it's an IVP. And then what happens is you have to find the interval of validity for an initial value problem or IVP. So you have to find the boundary of like your solution in essence.
okay,
But
so
if you guys didn't cover it, we're not going to cover it.
Yeah, but I mean, if it's on the review, it's most likely on the exam too.
Okay, I didn't really see that one here. Let me see.
'Cause I
What about
mean,
like in terms of like algorithms, like the one, first order, homogeneous, and that's like integration factor. Yeah, you're pretty good with those, right? And then the second order, this is the
uh,
integration factor,
integration factor.
and this is for first order. First orders are the easy ones where you're obviously given like the differential equation right here, and then you're also given the initial condition.
So I really don't feel comfortable with integration factors either. Is integration factor an e to the integral of
Yeah,
kx
it's
dx?
so like for example, like just doing this one. For example, if you had like this guy, and this is your differential equation. Uh, the one thing that you need to find is that so the if is like you do this, you do the exponent of the this guy right here, the thing in front of the zeroth order. You
Okay,
put it
just in front.
inside, and then you take the d, and then whatever this is, um, it's e to the minus x squared. This is your integration factor. So that's the first step for these ones. So after you get that one, then you have to multiply it on like the both sides of your differential equation. So like for example, usually this is the way I do it. So you have this guy, right? And then you have this y. All right. Actually, I'm skipping a step. Let me write down this guy first. Like y prime minus 2xy equals 2. And then this right here is just the hardest part about this is looking at the left hand side and seeing there's a product rule in here. So you have to do like a reverse product rule if you remember doing that. So you do like this reverse product rule, and then you do 2, and then you times this integration factor on this side as well. And then with that, you just pretty much I think if you actually do this one, it's like a weird one. You got this earth function plus c.
Okay, what is the error function?
So this thing right here is just what this guy is. Have you seen this earth function before?
It looks familiar, but not really.
Yeah, it's just the way like this guy is. If we there's probably an easier problem. This is like one of those like weird ones where you get like when you do this, you get an earth function on the right hand side. But essentially the method is just you get the integrating factor, you look at the left hand side, and then you do this reverse product rule, and then you times the right hand side by your integrating factor, and then you simplify it to this, because you need to get the y. You need to get the y. So you times it by the reciprocal of this guy to isolate the y. So let me see. So that would be
Okay, so how did you get the, I mean, after you finish writing, I'll ask you.
okay. Yeah, you times it by this. And then you should be able to transfer that over in here. Earth x plus c e to the minus x squared. And this is your general solution because you have a c here. And then like this method is really simple because then you don't have to do all the, it's like 1, 2, and that's it. You rearrange. And then you just apply your initial condition.
How did you get that at the very top? I understand the integrating factor itself, but how did you get the y prime minus 2xy?
The y prime minus 2xy. This part right here,
Yeah,
like from here to here.
or both of those.
Okay, this is the original equation. This right here is the original equation that we have. That's the left-hand side.
Okay. And then your
And,
y prime. How
and then
did you?
you have to do the reverse product rule.
I don't know how to do that.
Yeah, that's the most complicated. If it is complicated, like this is how you do it. So you take a look at this guy, y prime minus 2x, and then you have y. And then if you, let's see, if you did like ex squared y, you did this guy, and y prime e minus x squared, and it would be like minus 2x e minus x squared y. So this is after you actually like do this, because you had to transfer over that. So you know how in the first thing you do is you have this guy, right? And then you times it by this e to the minus x squared.
Mhm.
And then so you distribute the e to the minus x squared here and here. Minus 2, and you're going to get something similar to this. So minus 2x e to the minus x squared and y, and equals 2e to the minus x squared.
Mhm.
Yeah?
Yes.
Okay. And then so looking at this left-hand side, you have to look at that there's a reverse product rule here. So like, look at this, y prime ex squared. 2x minus 2x times e times to the minus x squared times y by itself. That looks like a product rule, right? And that product rule, so you have to like train your brain. Like that's the hardest thing about this integrating factor. It's not really hard though. Like you can get used to it if you train your brain to see that there's this guy coming in here. There's this going on. This is the reverse product.
Mm-hmm.
And after you do that, then you just do this, because you have to simplify this somehow. And then let's see. And then so you take doing the long way of doing it. You take this guy, y prime dt. Is this dx? Oh, this is dx. And then like the other side as well. You do like things like 2ex squared dx. And this is why you're going to get a c on the right hand side. So when you do this, the derivative cancels out. So the only thing left is this. That's how you wanted to do that product rule, because then it just pretty much cancels out the prime. And then if you actually do this integral, sometimes it's an easy integral. Other times it's not. This one gives you an ERF function. Plus,
How do you know it's an ERF?
that's the thing. You don't really. Once you see it, like look for the integral of this guy. I don't know if you can look up that somehow, or put it in your calculator. Wolfram. Let me see.
Is it because of the negative there?
It's just one of those like tables that you have to look at. This is actually one that's familiar. I've seen this before. So integral of e to the minus x squared. Let's see. Yeah, you're gonna get an ERF function. 2, yeah, e to the minus ex squared. Yeah, that should be the one. What did they get?
Well, I mean, I can see there being a no, not an it's not integrable, but it could also be square root of pi.
It's square root of 5 times the earth function, though, right?
Let me
That's
see.
what I'm getting. It's 2 times the actually it's not even the 2 is not even there. Actually, if you take out the 2,
Yeah, because
it's
it's
1/2.
related to Gaussian integration. From negative infinity to positive infinity, you get square root of pi.
And then so it's square root of pi earth, right?
No,
You get
just
earth.
square root of pi. I
It
just
just gives
think
you
it's because it's a non-elementary function. So I'm guessing.
the thing is, like, having something like this, it's probably not. It's pretty weird that he's giving you a review on this because you wouldn't know, right? That it's this
Yeah.
guy or this guy. You wouldn't know. So
Yeah.
if you encounter something like this, where like don't beat your head against the bush, or like because of this, because you can't do this one by mentally.
Mhm.
So what I would do is just do this side and carry on the integral. Like put
Yeah.
something in here and just that you're gonna have a plus c, but you're probably not gonna be able to finish it, yeah, because then you actually have to know what the general solution is.
Mm-hmm.
Yeah, hopefully he doesn't bring up something like this. That would be brutal if he brings up some earth function. But do you get the concept though?
I mean, kind of.
Yeah, because after we're done with this, if this is an easy integral, after we're done with it, we'll just go with what they gave. So earth x plus c. You just divide. Let me see what. Because you have to take out the other guy. That's even weirder. So if you did this, I think there's a mistake in their answer actually. Because if you divide it by the e to the minus x squared, then it would be y 2 e to the x squared earth x plus c e to the x squared. It's not negative because that's the only way you can cancel it. And this is your general solution.
Mm,
Does that make sense?
I don't know.
So like let's try finish the problem though. So getting to this point from the integrating factor, and it's been a while since you guys touched on first order, but let's try something that like I can come up with, and like an easy one.
It's just
And
this first half that I don't get. And the
the
fact
first
that,
half.
yeah, the
Okay.
first half of the material like covered, which was kind of like before like we started working on stuff.
Yeah, I know. It's fine. Let me cover this one. Maybe just like a few problems that I can like come up with. Let's try do this one. I think it's integrable. It's easier. So y prime, your differential equation here is t y prime, and then a lot of times the first order is actually easy, relatively easy when taking like variable coefficients, because you just have to apply the integral thing, the integrating factor. And then so your IC would be like y1 equals 1/2. So are you able to write this down?
Yes, let me just,
Okay.
I've just kind of been watching, but I'll write it
So,
down.
so like we can go over it.
Okay. Initial condition y1 equals 1/2. Okay.
All right. So the very first step for these guys is you want your y prime, your first order term, to be in the correct form, meaning like this thing has a 1 coefficient. So you have to divide everything by whatever coefficient is shown here so that this guy becomes 1. So correct form, I guess, correct form. So that would be like, I'll just write it and I'll divide the whole thing by t equals t squared. Yeah, t squared minus t plus 1. So you have to divide the whole thing by t so that it's equivalent. So y prime plus 2 over t y equals t minus 1 plus 1 over t.
Mm-hmm.
Did you get that one?
Yeah.
Okay. That one's just algebra. Okay, so you have that guy. And then the second thing is now you apply the integrating factor. So integrating factor. Integrating factor would be
To 2 over t.
You could do it like I usually just like calculate separately. So like this guy. So e and whatever is the coefficient in front of the 0th order term, you put inside the integral as the integrand. And then so you solve for the simplify it. So that one would be e, and the integral is 2. You've seen this before, ln t.
Mm-hmm.
So that's your integrating factor. So the next thing here is, so if you remember your rules of like logs, you can actually simplify this further. Let me see. So if you remember this 2 right here,
Yeah.
you can make it a squared, right? So like e ln, and you put the squared instead of like a coefficient 2. And then so with that, now you can cancel the e, right?
T squared.
Yeah, you cancel out the e, and then the only thing you have left is t squared. That should make your life easy. So that's your integrating factor, t squared.
Okay.
And then we do the same thing. So we go to, we have to multiply, right-hand side, or left-hand side, right-hand side of differential equation by integrating factor. So our equation, the differential equation was y prime, so y prime plus 2t y equals t minus 1 plus 1 over t. You times it by this guy. And so just simplify t squared y prime plus 2t y.
Oh, so you don't put the t squared in front of the original function, it's the simplified one?
No, you have to multiply it through the function, both sides.
Okay, because I got the first one, I got t cubed y prime plus t squared 2y equals t to the 4th minus t cubed plus
Which
t
one?
squared.
So
This is after plugging in the integrating factor into the original.
yeah, so you did this, right? Like you just times it through the original. Not the original, but the one where you have 1 as your y prime coefficient.
Oh, so you don't put it through the original. Okay.
Not the original, yeah. It has to be the one where the y prime. You could do that, but I would apply it to the one that we modified.
Okay, so t squared y prime plus t squared 2y over t equals t squared t minus t squared 1 plus t squared 1 over t.
Yeah. And then
Okay, so
what do you get?
t squared y prime plus 2ty equals t cubed minus t squared plus t.
Okay, good.
And then I guess you can't really simplify this. I mean, you could pull out the common factor t.
Yeah, I wouldn't. For the most part, you don't need to worry about simplifying this guy. Just leave it the way, like expanded. So like we have to worry about this guy though. So the next thing after you times it, the integrating factor, you have to look at the left-hand side and then see if you can see a reverse product rule. So is there a reverse product rule that you can do?
So there's two pieces. There's the, I mean, it's added, so t squared y.
It's this guy, yeah?
Yeah, you could do a reverse product rule here.
Yeah. For the most part,
Except I don't know what the y prime becomes the y. Wouldn't it just be 1?
the y prime for what?
Oh, wait, never mind. The y becomes the y prime.
Yeah, the y becomes y prime, yeah.
Okay.
It's
So this
pretty
is
much
the
just like
product rule.
product rule. So you do that, and for the most part, a lot of times like these are just manufactured. Like this doesn't work every time. So, but then the ones for the test obviously is gonna work. The ones that are given to you. But like I never did like this integrating factor thing because like how come you can always see a product rule here? It seems very manufactured. So you anyways you do that, and then the next thing you do is you take the integral. You take the integral in terms of the independent variable. So dt. And then since this guy is already a differential, it's just the reverse of it. So it cancels out. And then so the only integral you have to actually calculate is the right-hand side. So if you actually did the integral, it would be this. T squared, and you have a c because you need that for your initial value problem. And okay, did you get this first?
Minus t squared plus t dt. So the t squared y prime just becomes t squared y.
Yeah, you know why?
Well, it's a derivative
Yeah.
dt. So
Yep.
does the derivative and the dt cancel, or does the integral and the derivative cancel? Like,
It's pretty much the same. What you're saying is the same. So the
okay.
integral right here and the dt, they're all together, yeah.
Mm-hmm.
This is all part of like the integral.
Oh, okay. Right.
And then this guy is just the derivative. You could write this another way. Like you could technically, let's not worry about that. I might confuse you. Like I would just like every time you have the left hand side, and it's after you reverse the product rule, you always have a prime there. So since you have a prime there, taking the integral of that will cancel it.
Mm-hmm. So minus t cubed over 3 plus t squared over 2.
Yeah.
And I guess plus an arbitrary constant.
Yeah, because it's not this is an indirect integral, I think, or improper, something like that. Okay, so with that, or not definite. There you go. And then so with that, the next thing is you have to make this disappear, right?
Yes.
And then so
Wait.
this is the easiest.
Yeah,
This is the easiest step.
simplify the y. Okay.
The hardest step is pretty much like far beyond us, which is like just this thing. All of this, the reverse product rule and the integrating factor. And then so just 1/4 t squared, 1/3 t plus 1/2. And then you have this plus c. And from here, you know how to do the initial value problem. Like after you get the general solution,
Yeah, you would
just
just plug in stuff.
you just plug in stuff, yeah, like this, right? And
Hmm.
then from the y1, you should get this whole thing. I'm not gonna show it. You should get c equals y over or 1/12.
Okay. Yeah, that's real clear. I do think that
Okay.
this is probably a good way to actually do tutoring. Just kind of
Okay.
have types of problems and then just kind of work, kind of I work alongside you
Yeah,
because
it's
the
always good that way.
the
Yeah.
other sessions are just kind of it never really stuck, but this really does help this
Oh, like
style.
actually doing the problem.
Yeah, but the thing is that I would attempt a problem, but I would just be too overwhelmed with the information because the his tutoring, I mean not his tutoring, but his lecture videos
Yeah.
just didn't I just couldn't
They're
follow
stuck.
it.
Yeah. I don't know how he teaches. I saw that one video. I think you sent me a video, right? I think
I believe so.
that one video because it's like a YouTube video, but then I never actually listened to it. I don't know if he goes really fast, but that's fine. A lot of times it's like that. Uh, but we'll do our best to like reinforce, obviously, like.
Right.
And then like in terms of like the reviews, yeah, this is a good time to actually like hone in like which parts that you need to like practice.
Hmm.
Do you want more of this guy? The first derivative, first
I mean,
order.
that for if for that kind of form of, I guess, problem, that does make a lot of sense to me.
This is
Um,
problem. This problem. Okay.
yeah, and I mean, seeing the reverse product rule really doesn't bother me. Actually, I think it's super interesting the fact that it
That you
literally
can
is a
reverse it.
product rule backwards. Like you
Yeah.
don't see it and it just appears.
Yeah. That skill right there, you're gonna need that for like if you're gonna take higher level, I guess math or like
Okay.
whatever classes, you have to do that. They don't obviously calculus 1 and 2. They teach you how to do the regular way, right?
Yeah.
But then the reverse of the rules are also valid, which oftentimes, it will like when you're trying to prove something or like derive an equation for other times, yeah, that skill is good if you can see the reverse product rule because it's not only this time. There's a lot of equations out there that you have to use that.
Mhm. Like reverse, I mean, reverse quotient rule.
That one is harder to see though, the reverse quotient rule.
Okay.
If you think about it, like this, the quotient rule is like the probably the one that people don't like
Yeah, and I mean,
that much. The
reverse
reverse chain rule,
chain rule is just an integration by parts, right?
yeah, the integration. You're just pretty much applying integration.
Hmm.
But the reverse product rule, that's the one that like, that's used a lot. Like for this. But I still don't like this kind of like first order. It seems like for you to be able to reverse the left-hand side, seems like it doesn't really reflect reality, Like how many things can be reversed that way? I don't know.
Hmm.
Okay. So that's the integrating factor. Did you want to cover the VOP, the variable parameters first?
Yes.
Okay, that one is it's not bad, but let's take a look at what the problem is first. Actually, like at first last time I didn't let me just finish this. So this guy and then other ones.
Yeah, I'm just finishing the simplification step on the previous
Okay,
thing. So, I mean, when we simplify, we don't need to divide the c by the t squared, right? That stays.
you
The
don't need to
c.
divide the c by the t squared. You do have to divide the c by the t squared. Yeah,
Okay. Okay.
and then when you solve for c, just plug it in.
Hmm.
Okay, so like for this one, I thought at first I wasn't gonna like be able to look at number 3 is actually the hardest one for this from problem 22.
Okay.
But they actually give you a shortcut. They give you the solutions already, which is easy. But if they didn't give that to you, then life would suck. Because do you remember applying reduction of orders?
Reduction of orders sounds familiar, but not familiar
Okay,
with the process.
so reduction of orders. Oh yeah, this one maybe I'll do this one. So like we'll do a problem with reduction of orders plus the VOP.
Okay.
So because this was the hardest one. Like if you remember, I was talking about like reduction of orders is applied when you're doing variable coefficients. When you have like
Right.
it's not constant. For the most part, it's constant. Most of these problems have constant coefficients on their second order equation. But once you have like the independent variable times the second order differential equation, then it becomes variable. And then that's the time when you apply the reduction of orders, which
So
is
like
really,
an XY prime.
yeah, xy prime. That's definitely the one, or ty prime.
Mm-hmm.
And for the most part, like I think it would be best to be prepared to actually, because that's the hardest problem, to be prepared to at least like know the steps for that problem. So that's what we'll cover it next time. But like for all the problems, mostly, you only have to worry about constant coefficients, because that one's easy. We covered like repeated roots, and then complex roots, distinct roots. That's all you need to do for constant coefficients. And then when you're finally solving the a non-homogeneous equation, we covered last time the undetermined coefficient, right? We did undetermined coefficient.
Undetermined coefficients.
Yeah, I call that
Kind of.
UC. So VOP is a variable of parameters, and UC is undetermined coefficients. These are both the only, maybe there's like more, but then standard wise, these are the two algorithms to solve a non-homogeneous second order differential, or like third order, fourth order.
Okay. Would it be possible to try to review the undetermined coefficients, mainly because I was just not having a good time last
Yeah,
time?
there's
Okay.
there's a bunch of problems here that we can do.
Yeah, definitely.
This
Okay.
is actually the easiest one.
Oh,
Like if
great.
you were to pick between a VOP and a UC,
Hmm.
I would do the UC.
Okay, because that's just a YP and YC.
And then the YP is from that table, right? It depends on the table guess.
Yeah.
So that one, if the reason why UC is a better choice, because it gives you the most solutions. The VOP, you have to do a bunch of integrals, and sometimes the integral it's not integrable, so it can't
Oh,
be done. So that's why VOP is actually limited
okay.
in its applications. So let's see. Let's do the first one here, the number one. So I have that right here. It's actually this is like one of the problems I did. So did you do this one or?
C equals 112. Okay. Yeah, I just figured it out. Yeah, I got the C equals 112. So that's good.
Okay, that's good. Maybe for
Okay.
this, do you want to do this with me? Maybe like this problem.
Yeah, that would be good.
Okay, let's write the problem first. I'll just
Okay.
write over it. It's pretty much this one is just 2y prime
Mm-hmm.
plus
Prime.
18y.
So double prime, right? For the
Oh
two
yeah,
Y
double
double prime.
prime. 2y
Okay.
double prime, 6 tan, and then 3t. T is your independent variable here.
Mm-hmm.
So this one is definitely homogeneous, and it's second order, but it has variable coefficients. It has constant coefficients, which is easy. And then this one, he wants you to do this using variation of parameters, VOP. So very first step for all these like non-homogeneous type of problems, either VOP or like UC, you always want to find your homogeneous or your complementary solution.
So that would be, you would use the right side of the equals.
The left hand side.
Oh, left hand side. Okay.
Left hand side equals 0. Yeah, the homogeneous.
Okay, so 2y double prime plus 18y equals 0. And you would use the k's. You would basically put it into
Yeah.
general solution?
Yeah, the characteristic, and then you solve for the k.
Okay,
So you have this 2k squared, and then you have plus 18 equals 0. And then I would isolate the 2k squared, so divide by 2. And then so you get this polynomial k squared plus 9 equals 0. And that's it. You just take the square root. And this time, like, this one always, like, sometimes, when you're tired, like, oh, is it really imaginary? You have to be careful. So this is definitely imaginary, complex.
Because you can't get a negative. So
Yeah.
that would be, oh, you got a lot of company. So this is going to be I plus or minus 3, right?
Yeah. 3i. So this guy, if you remember, this is the term in front of your e, right?
Yeah.
It's this guy right here. And then this guy is a term in front of your cosine and sine.
So 3i. So then this 0 would be, you have to turn the tan into a cosine and a sine?
Oh no, you don't have to do the what one? You have to turn the which one?
So you focus on since it's a 0 plus or minus 3i,
Yeah,
that 0 replaces what in this equation?
this guy. It's the term in front of what you're raising the exponent or the exponential to.
Okay, so it's going to be,
This guy
since
right here.
it's the second derivative, you would have two arbitrary constants here.
Yep, that's what we have. Yeah, C1, C2.
Okay, so the 0t cosine 3t.
And it's really easy when you have this 0 term. So this one goes to 1.
Sine 3t. Yeah, so then this E0 is 1.
And then your complementary solution would be just this guy. So this is the easy part. Now it gets hard from here. I feel this VOP is the one that's something you probably won't like. But every time you have to do like an integral, it's always the one that takes a while. Like the integrating factor, it kind of reminds me of that. Okay,
so
you got that part?
So YCX is the C1 cosine 3t plus C2 sine 3t.
Yeah.
Okay, and that's just because we have a tan?
A tan?
Because like a 6 tan 3t?
Oh no, that's totally the 6 tan 3t is not. We're not counting for this. It's a 0 here, right? We're making because this is the homogeneous equation that we're trying to solve here.
Okay, is that just the form? It could be anything on the right side will always have a cosine and a sine?
No, it's so this is what we're trying to solve here. The reason why we have a cosine and a sine is because of our characteristic equation.
Characteristic.
The 2K k right here?
2k squared plus 18. So because we had an imaginary, we would have a cosine
This
and
is our
sine?
roots. Because we have complex roots of our characteristic equation, it gave us this Euler equation. The Euler with the e and the cosine, yeah.
Okay, so if let's say we just had like just we ended up not getting an imaginary, then
Okay.
what would our...
So you have like 3 things that can happen.
Okay.
So you can have this imaginary root, or you can have this root become maybe like you have 1, this, and then another root is like 2, and this is what we call distinct.
Oh, right. Okay. Distinct
real roots.
Real roots.
Yeah. These are all homogeneous equation algorithm for second order homogeneous equation algorithm. So when you have the distinct real roots, your general solution, your complementary solution looks like this guy. C1 e to the 1x plus C2 e to the 2x. That's your solution. And then you also have this other guy, which is called repeated real roots, where you can probably have like a k equals like 1, and then your multiplicity is 1. This is when you have this type of case. Your polynomial becomes this, or like you have a square there, this guy right here.
Mm-hmm. And you would still have the same, you would only have one solution. What, I know you already probably went over this, but what exactly is the multiplicity? That's just a kind of a...
I remember, I think this is actually a 2. This might be a 2. This multiplicity is just this exponent here. This is how many times this thing occurs. This is how many times this thing occurs. Yeah. But that's why you have repeated. That's why it's called repeated real.
Right. Okay.
Because then when you have this k minus 1, it's actually k minus 1 times k minus 1. And you can't just put the solution for one of them. You have to put the solution for both of them. Or else it won't be the right solution. But then, so for this repeated real roots, the general solution or complementary solution for the second order homogeneous equation is ycx c1 e to the 1x plus c2, and you put an x in the front right here, e to the 1x.
Mm-hmm.
And then this thing right here, this can grow. So what if you had like multiplicity of 3? What if there's like k minus 1 cube equals 0?
You would have then 3 c's.
You have 3 c's. So for example, this guy, and then you have an x still. You still have the same thing. And then the third one, the third fundamental solution, you have this guy is a squared now, x squared e to the 1x. And there's a pattern. Obviously, there's a 1 here, there's an x here, there's an x squared. Technically, this 1 is like x to the 0, so.
Okay, so it's like you're integrating it.
Almost. Exactly, yeah. And then this complex one, the one that we just saw, complex conjugate, complex imaginary roots. This is just the one of the form where you have maybe, what if your k was like this? You had 2 plus or minus 3i. And that's the roots that you have to your characteristic equation. Then this is the form of your homogeneous or complementary solution. It's the Euler equation. So it's C1 E, whatever this number here, you put it as the exponent for your exponential.
Mm-hmm.
And then whatever this number is in front of the I, you put as in front or inside the cosines and sines. And eventually, yeah, you're gonna just memorize these guys. This is the one that lingers, like the homogeneous equation solutions. People tend to forget the integrating factor one, and then all the other ones. Okay.
3x. Euler's. Okay.
All right, does that make sense? Those are the ones that are probably the core things that he can give you on the test. So,
wait, the 4 things, or?
Oh no, the core things, like probably the main bare bones that he can give on the test. This is the one that's like
okay.
Core.
I thought you said the number 4. Okay.
Yeah, no, I know. Okay, so with that, that's pretty much step 1. It's just knowing your homogeneous solution.
Okay.
That's the easy part. Now the particular. The particular solution is quite interesting for the VOP because you don't have to guess it. You actually have to manufacture it. And then there's an algorithm, systematic algorithm, but it is quite, it's not tedious, but it could get tedious though.
Okay.
And the reasoning why, so the very first thing you would do is knowing what your complementary solution was. Yeah, you have to take a look at like the fundamental set right here, this guy.
Yeah.
And then you write them as like y1 and
Okay.
y2.
Y1 is cosine of 3t. Y2 is sine of 3t. Okay, and you make a 2 by 2, right? Because it has two y values.
You got it, yeah. I wanted to touch on something else first because like the very first thing is I always gather what you need before you actually do the math.
Oh, definitely.
Because
That
then
physics
you're gonna be
taught me
like,
that.
yeah, exactly. So why the one thing, the couple things that you need is the y1, obviously, the y2, and
2
then the other thing is this r guy.
RT. Okay.
This is the right hand side, right?
Okay, right hand side.
Yeah, the right hand side of your differential equation, and that was 6tan 3t. 6tan 3t.
Okay.
All right. So once you have all the givens, now the last thing you have to calculate before you can do all these like integrals is the Wronskian.
Okay.
Wronskian comes in and you actually finally apply the Wronskian, not just like, use it to check. So in this sense, it's easy because it's only a 2 by 2. I think 23 is the one that's hard because it may take long for an exam. So yeah, you know how to apply Wronskian, right?
Yeah, so we get the y1 prime is going to be negative 3 sine of 3t, and y2 prime is going to be 3 cosine of 3t.
Yeah, that's right, yeah.
And then we put that in a Wronskian. So determinant of this would be 3 cosine squared 3t, or yeah, and then
Yep,
subtracts a negative
that's
3
positive.
sine squared 3t, which is just going to be positive. So
And you're going to see something interesting.
3 cosine squared. Is this like a identity? The
Yeah,
cosine and the sine.
yep, yeah, so it's
So that
1.
just becomes 1. Okay, so that's going to be plus sine 3 sine
Yes,
squared 3t, which then just becomes 3 times 3, or
okay,
or
3.
just 3.
Yes, 3, yeah. So you got 3, right?
Wait, so how? It's just like, how do you break that down? So the cosine and the sine becomes 1.
Yeah,
So you can pull out the 3's out of both, so it just becomes 3 times the cosine squared plus sine squared. So that becomes
yeah,
3
and
times 1 is
factor,
3. Okay.
or factor it out. So that's
Okay.
3, and then times 1. And then so your Wronskian is not 0. What does that mean?
So since it's non-zero, then we have
It's just a review question because it could come up.
yeah. Um, is
What
it
does that what does that tell you about y1 and y2?
y1 and y2 are, well, it's what, homogeneous? No.
Linear what? The first letter is L. Linearly.
Linearly independent?
Yeah, you got it. If it's
Okay.
non-zero, it's linearly independent. Yeah. Okay, that's good.
So
All right,
Wronskian is
which makes
3.
which makes sense because then you won't be able to actually expand this if it was linear dependent because then they're pretty much the same thing. So
Yes, that's
the next step is really difficult. Well, people see it, not really. Like I think the more difficult one is probably the reduction of orders, but this one is kind of like the integrating factor, kind of, not really, relatively. But yp, after you have all of that, you have the Wronskian, you have the y1, the y2, the rt. Those are the 4 things you need. Now you need to apply the equation for the yp. You probably
So
have to memorize this.
yp, I mean, the idea is that you have a yp plus yc equals 0.
Yeah. So yp equals this thing for like variation of parameters.
Okay, so we
That's why we had to
have,
get those four things.
okay, so we need the, so let's see, trying to see what I was writing here. So we need our y1, y2, Wronskian, and right hand.
Yeah, all four. And then there's it's not really hard to memorize in a sense because the only like try and write this down like the equation right here, and then tell me like what's different about these two terms. There's only one thing that's different.
So you need four things. Your y1, y2, rt, and w. So if we had a 3x3, we would need five things.
Yeah, the 3 by 3 we'll cover that on like after this one.
Okay.
It's a different equation. I would probably think of them like as two separate things because
Okay, so it's
the equation that you're seeing right now this only applies for 2 by 2.
okay, so yp of t is negative y1 t times the integral of y2 t rt
Yeah,
over Wronskian. Okay, that's not too bad.
it's not too
y1
bad.
of
Yeah.
y2 dt. Okay, and then this would be plus y2 t y1 t rt over
On scan again.
Wronskian of y1 y2 dt.
Yep. So like if you look at this, what's different about the two terms? The two things being added. What's different?
Well, just real quick for that. So the idea here is that our goal was to find our YP.
Yeah, that's the goal. Yes. The YP.
Okay, so we were solving for everything. Okay, find YP. YP using variation of parameters. Okay.
Yep. Yeah. This is it's not bad once we know this equation. Once we know this equation, you just pretty much apply it.
Okay, so I'm just going to rewrite what we need again.
Okay.
Cosine of 3t. Y2 equals sine of 3t. R of t is 6tan. 3t and Wronskian of y1, y2 equals 3. Okay, so
Okay. So like first of all, like look at this equation, and I guess tell me what's different about the this guy and then this guy.
so one is being subtracted, the other one's being added.
That's one, yeah, and that's good in distinction. What about something else so that it's easy to remember? You only actually have to remember one of them. This guy, right? Like this guy's outside, this guy's inside. This guy's outside, this guy's inside. You just switch them.
Yeah.
Everything else is the same. And then like this guy, obviously the sign of them. So
Mm-hmm.
just remember it that way, so that it's like you don't have to like, oh, okay, what was that again? Yeah, like so. With that, now you just plug and chug,
Okay.
and then like see if you get like a solution. The other thing before we do the plug and chug, these terms right here, the ones outside the integral,
Mm-hmm.
although they're like functions of your, this thing, the integrand, or what you're trying to integrate from with respect to, although they're like terms of that, you don't put them inside the integrand. Like you don't like times them by the integrand. You leave them outside.
Okay, so you can't combine the cosine and the sine together
Don't
as
do that.
common.
Yeah.
Okay.
This is like I guess seems like it doesn't seem to work mathematically. Like why would you not do that? Like I mean, what are you saying? Like this one is dependent by this guy, but this is just how it works. The VOP works like this, and that's why there's this equation that you have to remember.
Okay. Look at cosine of 3t of sine 3t of 6 tan of 3t over 3
Yeah.
dt plus, I think just integration in general is the toughest part.
Yep, and that's why I
One
don't
to
like it. Like
sine
with
of,
the factor and then this guy. I don't know if for the other guy, it's actually the other guy's a little bit tougher though, too, right? The undetermined coefficient, because then you have to do some linear algebra, kind of.
cosine of 3t. Did we do the undetermined coefficient in this one, or was it the different?
We did it last time. Like we did it twice. Like the other time, and then like one more twice.
Yeah,
Do you remember like we did the YP? We got the YP, and then we plugged it in back into the differential equation.
yeah.
That's the undetermined coefficient, and you solve for the A's and the A1s, A2s, B naughts,
Okay, yeah. I'll
the alpha and
definitely,
beta,
yeah, I'll
alpha and
definitely
beta.
like to do one final review on that on
Yeah.
Thursday.
Okay. Yeah, that one is not that bad.
Mhm.
It's definitely like the one thing about these things, and you're probably noticing it now, is there's two things happening. You have to recognize what you're doing. Like what is this differential equation, right? Is it linear? I mean, eventually, yeah, you're gonna solve non-linear ones as well. Right now, we're all solving linear, but like if they're like second order and then like first order, you, and then like after that you say, okay, the second thing is, okay, now I know it's second order. Does it have variable coefficients? Does it have constant coefficients? Okay, it has constant. This is what I'm gonna do. Is it homogeneous? Is it non-homogeneous? Then like knowing what they are, then you could just memorize all these steps, right?
Pretty much, I would think so.
That's how these guys work. It's just pretty much a recipe of like step one, step two, and everything else. They're all algorithms.
Okay,
Okay.
so sine and tan. Trigonometric.
Yeah, they're pretty. I hate doing the when you do trig substitutions and then all that BS. Hopefully, you don't
Yeah.
have to do integration by parts. Oh man. Maybe prepare yourself for that, because like, what if it comes out in the integrating factor or the VOP? It's like one
Okay.
of those things like, oh, like if you have to do it for a certain occasion, just review it, integration by parts.
Okay, just you don't need to show me how to do it because I do completely remember how to do it, but how do
Just,
you know what an
okay.
integration by parts looks like? Like what would you look for
What would you look for?
to
For
know it was an
example,
integration by parts?
like this guy right here.
Sine to okay, yeah.
It's like two functions being multiplied.
Yeah. Okay. That's enough then.
Okay, but then like in terms of actually, I don't know if I actually did it here. I pretty much just like plug it in the calculator.
I mean, yeah, for the sine and the tan, what would exactly be your u or your dv?
For this one, okay. Let's see what I did. Let's see.
So it looks like you could choose either one to be the u or the either one to be the dv.
I can technically. I mean, yeah. This is a calculus question, but let's go with it. Let's So always the integration by IVP is always the one that gets people. The IVP.
Yeah, the u dv minus
Yeah,
integral v du.
that one is something. I mean, if at a certain point, if you do so like a lot of it, then it
Mhm.
gets it becomes natural. But then like if you just like see it one day, which is like what we're looking at right now. That's why for the exam, prepare yourself by doing a bunch of these IBP maybe
Yeah.
ahead of time. So like it doesn't become unnatural. So the very first thing is integration by parts. Let's try to do this one. So integration by parts, IBP.
hmm
And then so what we're trying to solve here is the sine one, right? Is this terms of x or t?
Sine of 3t, so I guess, yeah.
3t, and then tan t, tan 3t,
hmm
dt. And then so your u is your, I would just take tan as the u.
10. Okay.
It doesn't really matter, but like it's up to you. I would just use this.
Yeah,
I
because
think
they both have the same priorities. Would one be more simple than the other?
Yeah, I think this is the one that's more simple. So
Okay.
when you do this v prime, it would be
Sine 3t dt.
3t dt, and then like, so you just apply it, right?
Mm-hmm.
I mean, I guess this is du right here.
Du would become secant squared 3t, 3 secant squared 3t.
Let's see if I am even doing this. Secant squared 3t. I think the 3 is right here, right?
Yeah, 3 secant squared 3t.
I remember doing this. And then the other one is, hold up, this is dv. This is dv. I don't like dv. And then v would be -3, right?
Yeah, let me just.
Or -1/3, actually, -1/3 cosine 3t. And what was it again? Like uv,
Minus uv prime
v du, right? I think it's this one.
minus integral v du.
Yeah, u dv equals uv. Yeah, I think it's that one. U
V
dv equals
minus.
uv. Okay. And then so you just do this. Let's see, what is your uv? It would be -1/3 cos or tan 3t cosine 3t. That's your u and v. And then minus minus, so that's a plus. So that's v du. So minus minus v du. That cancels out. The 1/3 and the 30 cancels out. And it becomes secant squared 3t cosine 3t.
Okay, and that looks like you got to do it a second time.
Yeah, and then so the u again and dv. So you have this guy already, so just take this guy out. Just focus
Right.
on this guy.
Mm-hmm.
So what would you choose? Let's see.
Maybe u would be the secant squared 3t.
Actually, hold on. Let me think. Let me think. I think you don't even need to do it again. Actually, you don't need to do it again.
Oh, it's an identity. It's an
It's like one of those stupid things, like
double angle,
that
or
you'll never like remember it. But but what this is actually, if you do the so if you didn't do the that's like a lot of times like when you have the so make sure you have the negative right here. Make sure you have that negative still right here.
yeah.
So it's going to be this guy minus secant squared 3t cosine 3t dt. This is -1/3 natural log secant 3t plus tan 3t.
It's a trig identity, I guess.
Yeah, oftentimes when you have something like this, it's like really crazy.
Okay, so that's secant squared. Yeah, I'm looking. It doesn't look like there's anything trig identities related with the secondary trigs.
Let me see if there's something that we can look up. Steps. Okay. The one thing I would do. Let me see if we can do that one. Secant. Okay.
Secant squared.
Oh yeah. Oh, I think the one thing you can do. Let me see if I can show this. Is do this. The secant squared can be expressed in terms of cosine.
Mm-hmm.
1 over cosine squared, right?
Yeah.
Cosine 3t. This whole thing is squared. And then cosine 3t. There you go. You see something going on?
Cosine 3t. And
Yeah,
then,
these guys can cancel, right?
yeah,
They
so
can
you would
cancel, right?
get,
It would be like -1 over cosine 3t.
but can you do that through a square?
Yeah, because it's 1 squared over cosine squared. Yeah, there's nothing going on, right? This
Oh,
is a
right. Okay.
there's nothing like bad going on that you can't do math with.
Yeah.
Yeah. So this one, yeah, this one's still 1. So and then from there you just do your identity. So what is that? That's like reciprocal, right? So secant 3t dt. We know this one. For this, you probably have to do a u sub if you remember doing that.
Yeah, so your u would be 3t.
Exactly. Yep.
And then
So
du would be 3 dt.
and then so you need to do like was it du equals 3 dt, and then dt equals like 1/3 du.
1/3 du.
And then so you times this by 1/3 du. Yeah. Yeah, you have to sometimes like, so these, they all become natural at some point, but like for the most part, if you can use it, obviously math, you can't use your calculator, so you have to sometimes relearn them. So this one, this one, this one, this one, and then the next thing is, I think you know what this is now, right?
Secant u.
This one is now it's just one thing, and so this is where we get our natural log from.
Okay, so secant becomes natural log?
Yeah.
Oh, because it's not secant squared, it's secant, so you would have, wait, tan?
Yeah. It's tan
Oh,
u
secant
plus
x tan x.
natural log, yeah. Natural log. And plug in back the u. Plug in back the u, which is 3t. So negative 1/3 natural log tan 3t plus secant 3t. That's it.
Okay.
That would be that term. So trying to go back to that guy. So where are we? So that's how I got this guy right here. That's how I got plus 2. Oh, I see what I did. Okay. And then this thing, there's two things going on, right? We had the integration by parts, which is this guy, the UV. This is the UV from integration by parts. And then this guy is from the U sub.
Yeah.
This is the VDU.
Now we got to add together the first one with the second one.
Yeah. So yeah, that's why I don't like this VOP, because of this exact thing. Like you have to like come back to all those things that you should know, but same with the integration factor.
Okay. So then we just summing for these, you would have the 1/3 you would pull out, and then you would have just the sine and the 6. Okay. Could you also pull out the 6 too?
For which one?
So the sine 3t, 6 tan 3t, could you pull out the 6? Because it's basically the integral of sine 3t times 6 tan 3t over 3 dt. And could we pull out the 6 and the 1/3 out? Or just the 1/3?
For which one again? My computer was acting up. I
Oh,
didn't hear what
okay.
you said. What did you say?
Okay, so we had, in the problem, we had a negative cosine of 3t times the integral of sine 3t times 6 tan 3t over 3 dt. And of course, we had the same thing, but with the plus sign and another stuff. But you do the process the same with both. Could you? I know you could pull out the 1/3 out of the integral.
Yeah. Oh,
And
which
then,
integral? Which integral?
well, I mean both.
You're talking about this guy. Are you talking about this guy?
The like basically when we were solving the particular solution,
This guy right
back,
here? I think this is the one, right? The particular solution
yeah,
where we had the 1/3.
yeah, we
The
would
one.
pull out the 1/3 and also the 6, right?
Yeah, you could pull those up. I simplified it to 2, 6 over
To
3,
2.
2, and then I pulled it out, which was
Yeah.
like right here.
So that's a 2 times the integral. Okay. Of sine 3t, tan 3t. Okay. And you would do IBP on that. And
And then we did the IBP on like the integrands, and then we get this one. And then the other one, you don't have to do the IBP. You could just do the sine. The integral is sine.
okay.
Sine 3t. And I think this is that guy right here. Yeah, it's not bad. It's just one of them you definitely have to do IBP, and then if you have to do both IBP, that sucks. It's gonna take a lot of time. So I probably do
Okay.
VOP last and do everything else like first.
Okay. So, but wouldn't you have to do IBP on both because they both have a sine times a tan on one of them and then a cosine times a tan on the other?
The tan one, I would change it to a sine over cosine.
Sine over cosine. Okay.
Yeah,
So
the
you would
other
get a
one,
sine squared and then
which one are you talking about? The second term, the plus term? This
well,
guy?
no, like I'm just looking at what's in both of the integrals.
Okay,
We
for
can
one of the for one of them you're gonna get a sine squared, but I wouldn't do that. I would just stick to the tan.
wait.
You could do sine squared. Maybe that integral is like easier if you wanted to, but then you're gonna get a cosine at the bottom. So like you have a fraction like this guy, right? Like you have sine 3t and sine 3t over cosine, right?
Sine 3t over cosine 3t or
Yeah, and then so you have sine squared over cosine 3t, sine squared 3t over cosine 3t. But then I wouldn't do that though. I think it's like more difficult to do the integral if you have like a fraction in there. You might have to do the partial fractions.
okay, so then in that case we wouldn't want to do either.
This
You
one for the other guy it cancels out.
wait,
For the
so
other
we
guy,
do make a fraction and then
for one of them, if you make a fraction if you can cancel the fraction. If you can cancel the fraction, make the fraction.
oh, okay, so in that case that would be the second one we could just cancel.
Yeah. But if you can't, don't do the fraction because you might have to do the partial fractions, which is not good.
Okay.
Okay. Yeah, I don't think you have to do partial fractions in this. IBP is like the worst one.
Hmm.
Okay. And yeah, I think that's probably the hardest part. And then once you get the solutions for those, you just have to like combine them and simplify.
Okay, so after you do the integration, then you'll have yp.
And then so let me simplify it. Let's see. So once you do that, after you have all these guys, right? Then you do some simplifications. Try simplify it. Like after you simplify that
Hmm.
yp, then that's what you have. This is what you have
Okay.
right here.
Yeah.
And something should cancel out, which makes life easy.
So the cosine secant would you have so it's a yp, okay. Yeah, because I don't think you could cancel anything that you underlined in blue there at the bottom.
Okay, yeah, you should get that term. So when you get like this minus 2/3 cosine 3t sine cosine,
So let's see.
and then the other one is like which one is this? The minus the 2/3 cosine 3t tan, and then the times cosine. If you change the tan to like sine over cosine, then what happens is it minuses with the other term. Is that happening? Like, do you see that happening?
Let me see.
The one with the tan and cosine 3t. If you change the tan to sine over cosine and times it to the minus 2 cosine 3t,
Yeah.
That whole thing should cancel with the plus 2 sine 3t over 3 times cosine 3t.
Plus the sine 3t times integral of cosine 3t times sine 3t over cosine 3t. So it looks like the second one does simplify to just sine times integral of sine. So
that's the integral sign, which is like
negative 3 cosine
negative
of
1/3. Negative 1/3.
Negative 1/3 cosine of 3t.
Yeah. That one should cancel with the first term. The first term meaning that not the natural log. The natural log is the one that sticks.
Okay, so natural log. Yeah, because it's still kind of trying to figure out how to do the integration by parts part. But
okay, you didn't finish the integration by parts?
No, I just started to work on the
Try doing that still. Like we can wait. Like the IBP, what part are you in?
Oh well, actually, I was just kind of like thinking that we were just kind of explaining stuff, but so I didn't actually start working on integration by parts. So I'm just gonna start that. So we have sine of 3t, tan of 3t.
Yeah, I think it's good to review the IBP and then the U sub.
So then we would just take u as our sine 3t and dv as tan of 3t. Does it really matter which, like, I know it might make things more complicated, but can you choose either one to be your u?
If you did sine as your tan or as your u,
If you chose tan as your u, would
and
it
then
still be
tan
possible to solve it?
Let me see. So when you do the du right here, it would be cosine 3 cosine 3t. And then when you take the integral, it would be, what's the integral of tan?
That would be secant 3 secant. Well,
it's 1/3. Is it 1/3?
I think 1/3 secant of 3t.
Okay, that's what it is.
I let me just pull up the calculator.
Because I don't remember it. That's why I don't like doing that, because I don't remember it. The integral of tan x. It's the integral of tan x is you have to do a u sub. I don't want to do a u sub.
So
it's
tan x is a negative natural log of cosine x.
Yeah, it's that one.
So
either you know that or you could do a u sub. That's why it's like a more complicated version of it.
Okay, so I just pretty much kind of know it as like a table kind of thing.
Yeah, but I wouldn't do that one. Like you would do this, right?
Okay, because originally I thought you were supposed to do the easier one was making u sine. So you should
if you make u tan u, I think it's easier.
Okay.
But this u sub right here is still something that you still have to do a u sub afterwards.
Right.
Yeah. So pick your game. Easy now, hard later. Hard later, easy now. I don't know. I think either way, you just have to go with it.
Okay. So I just want to get the hard stuff done first. So I think I'll just stick with that. But I mean, as I was just wanting to confirm that you can choose either to be your u or v.
You could use you could choose either one. Definitely, that's up to the IDP is up to the person.
Okay.
But then like pick the easiest route.
Yeah.
Least resistance,
Mm-hmm.
Why would you want
that light bulb to glow brighter? But you don't want to trip the circuit.
Yeah.
Okay.
It's always the case. You definitely, like, in terms of the exam as well, like something like this, I don't like working in natural logs. It's a preference thing. Like I don't like, or you don't like working with secant, but secant can be turned to cosine.
Mm-hmm.
Okay, do you want to talk about the other one, like just to finish it off, the third version, the 3x3?
Yeah.
Okay. 3 by 3, which is a difficult one. Let's see. Let's look at this guy. So it's a 3 by 3 when it's like not a second order. It's gonna be a third order.
Third order.
Yeah, hopefully he doesn't give you like a fourth order.
That would be mean.
That'd be insane, yeah. But it's not bad though. I think you should prepare for it.
Yeah, but I mean, it's just more of the same.
It is. If you can extend it, the point is here is, can you see the generality? If you can see the generality, all things can be extended.
Yeah.
So okay, let's look at this one. So yeah, look at 23 number 1.
Okay.
23 number 1 is this triple prime plus this 1 prime y equals tan x. Okay. And then what you have to find is y of x. This is a general. I think this is a general. Yeah, it looks like this is a general solution. This is a general solution. Yeah, you're only supposed to find the general solution. So finding the general solution is easier. If you have to do the IVP, I think it's not that bad. The very first step is always find your complementary solution, which is when the right-hand side is 0. So this whole thing is when your right-hand side is 0, which is what we've been working for like ages of. So you have this guy, you do the characteristic, and then once you do the characteristic, you find the roots. And then you always get complex roots. For some reason, they don't like the other ones because it's like easy, I guess. So they give you complex roots for the most part. And then you apply Euler's equation.
Okay, why did you just get C1 by itself?
You get C1 by itself from this guy. So you have this k equals 0, right?
Yeah.
And you also have this guy. You have 3 things happening in the side, and you have to account for them. So you have k1 equals 0, k2, and k3. Oh, actually, let me separate this because then it'll be easier to see. Or, let's not separate because it's going to be the same thing. The other one is 0 plus or minus 1i, right? You had 3 roots, right?
Okay, so we get 2. Yeah, we get 2 answers. Yeah, that makes sense.
Yeah, and this 0, 1 is for this guy.
Okay.
Yeah. Sometimes when you go over a second order, yeah, you have to combine the 3 things that we talked about: the repeated roots, distinct roots, and then the complex roots. All right. So then after you do that, you get this guy. So that's good. The second thing is, let's find yp of x. And then the equation is different. So that's why I said keep them separate. It's not fully different. It's not fully different. It's just like this is the general equation for the yp, where you do this. So take a look at this. It's slightly different, right?
YP.
Try to look at this equation right here. Slightly different, right?
Yeah, there's no negatives.
There's no negatives, right?
Yeah, there's y1 is positive.
And then the other thing is you have this like weird Wronskian. What is this guy right here? What are these guys?
Those would be your ij and k.
For the Wronskian. So you know about the other ones, these other Wronskians?
Yeah, so that would
Okay,
be like
that's good.
for the first one, you would focus on column 2 and 3.
Yeah,
Second one, you would focus on 1 and 3, and
you
then
got it. Yeah,
3, 1
and
and 2.
you make it like 0, 0, 1, right? You
Oh, so
zero it
you
out.
do RF?
Not reduce echelon. It's just you just zero it out. In essence, it looks like that, but like
Hmm.
this right here. This is for like the first one. Every time
Yeah.
you do the first one, you zero it out. You put a 1 right here. The next one, Y2 or like W2, you zero it out and
Hmm.
you do the whole. Yeah, it's a little weird. Like I said, it's a little weird. And then the Y3, you zero out the column right here, and that's it. You want to go over it though?
Yeah, that would be helpful.
Okay, so the equation right here. Yeah, so the 2 by 2 is by itself. Don't combine it with this 3 by 3 or what 4 by 4, whatever it may be. If there is a 4 by 4, you just add another thing, just following the pattern. So like maybe Y4 R W4 over W
Okay.
dx.
So you do the full 3 by 3 determinant, but then you have to go back in and solve for W1 through 3.
Yeah, you saw the full determinant is this Wronskian by itself.
Yeah.
So once you do so this is the equation. You have to find each individual parts now. So we already have the Y1. This is from our homogeneous. Y2, Y3,
Hmm.
and then the R is just the right hand side. And then now we're only missing the Wronskian. So let's try to do those. So luckily, one of these fundamental solutions is 1. Yeah.
Hmm.
So the derivatives are easy, and I think the determinant is also easy.
Okay, so it's 1, 0, and 0.
Yeah. So you don't even care about these other ones. You just do this guy. You just do this guy.
Oh, okay.
Yeah.
Yeah, I was just wondering why it's 1, 0, 0. Okay. Yeah, I'm familiar with that then.
Good. Awesome.
I
Yeah.
was thinking I didn't realize that was 1 and you had to somehow turn a trig into a 0. And
Yeah.
okay.
But like it's actually not bad. It could get harder though, like this 3 by 3. Like I'm hoping it doesn't for the exam. He chooses like 1, and then so yeah, you just do this.
Okay. Could you show the other two? Like just like
Okay,
I want to kind of see what
so
the
the other one would
matrix
be,
looks like.
so you have this guy, and then you technically apply this, and you cross out that guy, and then it would be these, and then you go from here, and you go with
Oh,
that one,
okay.
and
So you go vertical instead of horizontally.
you could do vertical or horizontal. There's like different ways. But in this case, I did it horizontally because it's 0.
Hmm. Yeah.
Yeah.
Okay.
Either way, like if you did it horizontally, like right here, you zero these out. You go this guy. Whoops. You go with this guy or this guy. It's both 0, so it's gonna zero out your determinant. If you go with this one, this guy times this guy times it minus this guy, it's gonna be zeroed out. Yeah.
Hmm.
So that's how. Yeah. If you went with this, it's the only one that will be there. And then again, like some weird treg is gonna pop out, which makes life easier. And so you get this guy.
Okay.
And then like so that one is easy. The other ones are just something that okay, that's what you do. You probably done it already. So when you do the other ones, 1, 2, and 3 versions of the Wronskian, you just do this 0, 0, and then 1.
Hmm.
And then again,
0, 0,
these
1.
are zeros, so you only care about one minor or one part of the determinant.
So did you flip it around so that it's row 3, 2, 1 instead of row
It,
1, 2, and 3?
it's this way. This is the way I usually do it. This is the way. So for all of them, it's like this. Like you zero it out like this for all of them. 0, 0,
Okay.
1. Yeah.
Huh. I don't recognize that.
Okay, but this should give you the same solution. What way did you guys do it?
Well, like I thought that what from what you were telling me, you would just do the full Ronskin, but then you would focus on just the separate parts in finding the full Ronskin. Like you would, it's like if you had a three-step problem, the full
Okay,
three-step problem would be just the W at the denominator, but then like you would just focus on step one as being
okay.
W1, step two. Like I didn't know it was like a different process.
It's a different process. So when you're doing this W1s and W2 and threes, what you have to do is you have to zero out the way I'm doing over here. You have to zero it out, and then you're only left with like the third row as one.
So zeroing out.
The first and second of that column, whichever column you're in, which is the first column.
So do you have to do some kind of operation to zero them? Or
No, it's just an algorithm. You just do it like that. You zero out like whatever row, like Ronskin you have W1. You get this guy. You zero out the X or the first row, second row, and then the one would be the third, and then you do the determinant.
okay. And then it would basically for W1 it's 0, 0, 1. W2 would be 0, 1, 0, and then
For
W3 is 1, 0, 0.
for W2, it would be the second column. This number is associated with which column you do this.
Huh.
So for W2, still 0, 0, 1.
0, 1.
And then because it's W2, you do that for the second column, and then everything else is the same. Everything else is the same.
I don't know how to do that.
And yeah, it's just the way the that you do it. It's if I don't know if that's the way you guys did it. Is like what way did you guys do it?
I don't know how we did it.
Okay, but this is the VOP though. This is like along with any algorithm. This is it's like someone created this and then it works, and
Yeah,
then like
because I'm completely unfamiliar with what you're doing here.
the V. Okay, okay. So it's something that we have to just like cover. And for this one, all you have to do is like remember whatever the number is this is the column that you're gonna do this algorithm by 0, 0, 1.
Okay.
And we have a
So
couple practices that it will
when you say 0, 0, 1, how did you get the 0, 0, 1 that way? Because I know we do
uh
0, 0, 1 for each column.
okay, yeah, that it's like I said, it's the way you do it is you're not doing elementary like row operations for this. It's not like you're timesing it by something. It's you're just finding the Ronskin at that column by doing it. So Ronskin of this column, or this guy, and then for this guy it would be the second column. You do this, and in the third column you do this.
Yeah, I just don't know how you did 0, 0, 1. Did you just reverse the order of the first column?
No, that's just how you do it. Like even if this is a different problem, even if this is like another number, sets of numbers, you still do 0, 0, 1. You just do 0, 0, 1 all the time. It's not like something that you.
Oh,
That's why it's
okay.
easy. You
Oh,
just
so it's
put in.
just 0, 0, 1 always
Yeah,
for any problem.
any problem. Yeah, it's not like because my one of my rows is 1, 0, 0.
Okay. 0, 0, 1, okay.
Okay, and then so we'll cover the other one, which is kind of like I think it doesn't even have 1, 0, 0, 1,
Mhm.
which will probably make more sense. Let me see. Yeah. Okay. So after you do that, that's why this one is a little weird. After you do that, you just do the determinant to W1, W2, and then W3.
Okay, just a random question just aside from this.
Okay.
Have you ever taken mathematical physics?
Uh, what does that entail? It's not really like is it versus theoretical physics?
Yeah, mathematical physics is kind of like using mathematical concepts to solve kind of abstract physics problems. Just it's it's kind of like it's a very abstract, like it's proof heavy. You have to
Proofs. I've done like numerical, like linear algebra. It's not like numerical, like partial differential, but it's not like the physics I've taken is probably just analytical physics. Not like
hmm,
not like mathematical. Maybe it's the same. It's a different word, but it's different.
yeah.
Have you
So
guys do you guys offer that class?
no, I just remember reading about it. It's like there's I just look at the Wikipedia page and it's talking about like finding solutions of Schrodinger's equation for
Oh, I've heard
quantum
of
harmonic oscillators with their
yeah.
amplitudes.
Well,
It's
Schrodinger is actually I think it's like there's a numerical and then there's an analytical solution that I've heard of the equation. Yeah, I think it's a
okay,
quantum
yeah.
differential.
It's just developing mathematical methods for problems in physics.
Okay, it's
Uh,
I always like associate like the physics problem. If it was a physics problem, most of it is just partial differential equations.
yeah.
Like all these phenomena thing can be like the it can be presented in a part PDE. They call it a PDE. What we're doing right now is like ODE,
Hmm.
which for the most part ODEs work for certain like physical problems, like maybe stresses,
Yeah.
or but then yeah, you should definitely take one if you guys have like a PDE class. It's like one of those things which is really nice to take.
Yeah, because one question I've always kind of wondered is there a way to determine I guess, the force required to pull a spring at different lengths? Like
And,
if you have the
yeah,
amount of force, like force spring at initial tightness, and then pull it 1 millimeter versus 2 millimeters or something like that.
yeah, you could do that. That's a physical problem. What you would do, and then what do you want to know? Do you want to know the displacement or the force or the stress?
Like the force required or the work required to pull the spring
Oh, the work
given.
required. So that's a
Yeah.
thermodynamics problem.
Okay.
So thermodynamics, and then if you're gonna the work required, that seems like a problem that you guys are already working on because it's a mechanical, right? Like it's like a mechanical work.
Yeah, like, kind of like, or it could even be like, what is the strength of the spring? At
In terms of strength of spring, that would be like a strength. Like strength would be stress. So what you would solve first would be displacement. Like after
Mhm.
you pull it or pull the string, which is like a tension force, right?
Yeah,
So that tension force is
spring tension.
applied, and then after it's like an external force, so you're applying Newton's law, and then after you do that, you probably have to solve the like a like the displacements, and after you get the displacements, yeah, you figure out the forces, the internal forces, and then you can also solve for the stresses. And
So you could even theoretically calculate, like, I guess it is kind of similar to spring force, but like the amount of
it is
force required to break a spring.
it's exactly the same. What you're talking about, the spring is exactly the same as the string, but the string we consider that as like because everything if you're interested in that, like the mechanics of materials,
Hmm.
advanced continuum mechanics, like those are really fun. You get to learn like finite element analysis, which is like a way to like solve these problems for you to like find the strength of materials using like a PDE,
Yeah.
which is the elasticity. It's called elasticity, and then the other one is called thermal heat transfer and elasticity are two big things that you'll use. Like there's a world of like CFD. They call this computational fluid dynamics,
Hmm.
which is primarily just thermodynamics and heat transfer. You're solving for those types of problems
Okay.
numerically. And then you have finite element analysis, which is like solving for the elasticity problem, 2D, 3D, 1D, and then getting like displacements, deflections. And then from deflections, deflections are related to stresses, right?
Okay.
It's fun if you take those classes, if you're interested. That's when like physics very much becomes math.
Yeah.
And then like there's meaning to these numbers now.
Yeah, honestly, it's just like there's so much. Dude, math is such a huge field, and it's just like there's so many interesting problems that,
Yeah.
it includes chemistry and physics and, you know, mechanics and all of these different fields are all under mathematics.
And
It's just
that's why
huge.
if I were to like you know there's always three. I feel like there's three things going on. There's the theoretical, like the physics,
Hmm.
and then you have the quantitative, meaning like the math, right?
Yeah.
And then like when you finally apply it, like most of these things, rarely do you ever use like paper and pencil, right?
Hmm.
You
It's
you have
all,
to you have to use a computer.
yeah.
So once you get to that realm, then it becomes computational. Like quantitative becomes computational, and that's like the ultimate of ultimates. Like I would say, you learn the theory concepts in physics, you learn the quantitative mathematical equations, and then you finally apply it in the computer, which becomes computational. Which then at that time, you have to take in the computer science coding stuff, like MATLAB. That's why I say like if you like the stuff, go learn like MATLAB or Mathematica,
Hmm.
um, because
Okay.
because then, but then you don't want to be using that if you don't know how to do the the hand calc first. They call it the hand calc because the hand calc kind of informs you if your computer is giving you trash or is it good answers,
Yeah.
And then like it gets very interesting because then once you get to that point, like you get to solve problems that there are no equations to use. You can't solve like like a car impact problem with an equation only, right? Like you can't solve like maybe like a bomb blowing up and there's like a fire and
Yeah.
then you try and or multiple fires and then you try, there's so like science and math, like once you do the computational like CFD, if you ever see these classes like CFD and like finite element method, FEM, CFD, FEM, definitely take those because I think you'll be interested.
Okay.
Okay, so yeah. So does this make sense? I don't know if we finished this one.
Yeah, I mean, this does make sense. I just didn't quite understand what the 001 was supposed to be.
Okay, I'll probably cover like another problem like this next time.
Okay,
Let me actually put that down here.
and in general, the one will always be in either row 3 or column 3.
There, one would be column three.
Okay.
Not column three. Row three. It'll be row three, and then the number of the Ronskin is gonna be the where you put the 001 in.
Yeah, because I was just thinking because you mentioned that you can either do it horizontally or vertically, like row based or column based to solve these two.
Yeah. What I would do is wherever there's a one, this is a shortcut. Wherever there's a one and everything is a zero, you just
Mhm.
solve for that.
Okay.
Like the one becomes like where you stretch out your determinant. This is a
Yeah.
linear algebra thing.
Okay.
Okay. Okay, so I'll cover that next time. The Bernoulli and classifications, and maybe the this hard one, the reduce of orders plus the VOP.
Sounds good.
Okay, I man, yeah, I have other things to do, but yeah, please definitely send me like once you do all the rest of the problems, please send me like what you want me to cover more besides these four things
Okay.
on Thursday.
Yeah, I'll have to try because tomorrow is my chem exam, so
Oh
hopefully my
yeah.
brain
Oh, yeah.
won't be too fried.
Okay. Yeah. Actually, four of these things are already good enough. I think if we, for the most part, we covered the first order today again,
Yeah.
and then like the VOP, and then just practice after your exam on like tomorrow. Just practice a lot of these problems, and then I think that's what it is. Like you don't know what you don't know that you need to review, until you get stuck with these problems.
Oh yeah.
Okay. All right, bro. I'll see you on Thursday.
Okay.
All
Thank
right.
you.
Yep.